All right, with the videos we have seen, I think we're ready to tie everything together to actually state the central limit theorem, as well as the conditions needed to satisfy the central limit theorem, which we're going to need for the rest of the course. All right, so let's hop to it and let's actually do this. So let's come back to where we started. And I started off this whole bit by giving you a recipe saying one of the ingredients for this recipe was a handful of almonds. I asked, how much is a handful of almonds? I said, well, let's take a sample. And we created a distribution. That distribution might change from one person to another. And we said, well, that distribution, we said, well, I just kind of assumed it's going to be a normal distribution. Does the distribution have to be normal? Does the original distribution matter? Can it be uniform? Can it be skewed? Can it be bimodal? Can it be binomial? I don't know. Can it be something else? Shall we find out? Okay, I have a simulator here that will help us to actually see this. So let's actually check this out. Can I make this bigger? Let me see. Yes, I can make it bigger. Perfect. Let me actually make it wider. Perfect. All right, so the way that this simulator works is we have a population here, and I will take individual measurements here, and I will show the average of my individual measurements here. And this will become my sampling distribution. Let me show you. So currently I am taking a sample of 5. Okay, so you'll see individual measurements, 1, 2, 3, 4, 5. I take the mean, there it is. That's one sample. Now let's take another sample, 1, 2, 3, 4, 5, and there's the mean. I take another sample, 1, 2, 3, 4, 5, there's the mean. And I could do this over and over. I can do this all day long. And I will just build a collection of mean values. And these mean values will collect and form my sampling distribution. And you kind of get the idea. I could just keep doing this all day, and I can bore you guys to tears, and I'll run out of video time. But I'm not going to do this all day. So I have a shortcut here. I can do 5 at a time. So there are 5 more at a time. I just add 5 more sample means, 5 more sample means, 5 more sample means. I can just keep doing 5 more at a time. And you can see it building bit by bit. Or I can jump the gun and just say, let's do 10,000 or 100,000. So now I have 640,210 samples, and I took their means and created a sample distribution right there. And you can see, sure enough, it forms a normal distribution, and the equations apply as I showed you with a mean and standard deviation, the equations that I showed you in the last video. Great. Now that worked for a population that started with a normal distribution. But will this work with other distributions? Let's clear everything out. And let's say we start with maybe a uniform distribution. Maybe we're rolling dice, right? Because dice have a uniform distribution. All right, let's start it off. Let's say we roll dice 1, 2, 3, 4, 5. There's a sample mean 1, 2, 3, 4, 5. Again, I'm not going to waste your time. Let's just cut to the chase. Okay, and we'll cut to the chase and go. And, well, how about that? That's looking fairly normal right there. Not too bad. That looks pretty good. Okay, well, let's try something else. Maybe a skewed distribution. So we get our sample. Cut to the chase. Let's just do this. Well, that almost does it. That looks good, sort of. It starts off looking normal, but this tail looks a little bit long. Okay, so it starts off looking normal, but it does sort of resemble the shape. Okay, but I think I can fix that. What if we increase the sample size? What if I increase the sample to 10? So let's clear everything and then start building up our sample. Oh, you can still see it. It looks pretty normal, but it still looks like there's a bit of a tail there. But it looks better. What if we increase it to, let's go to increase it to 20. Definitely looks a lot better. Maybe there's a bit of a tail there, but it definitely looks a whole lot better. Remember, did you notice what's going on, by the way? As I increase the sample size, did you notice how my distribution is getting narrower? We talked about that in the last video. As my sample size increases, my distribution gets narrower. My sampling distribution gets narrower. That's what's going on here. There we go. Sure enough, this is starting to look pretty normal. Pretty awesome. Okay. What if we create our own? Let's create something that's bimodal. Okay, something that's bimodal. And we'll start off with a small sample size. Okay. Well, it doesn't look too bad. It does kind of look like it's flat on top. It doesn't quite look normal. Not too bad. But if I increase the sample size, we'll go n equals 16. Oh, that's already looking pretty good. Maybe a little flat on the top, but if I increase the sample size, yeah, that definitely looks really good. Okay. So, bottom line here is that no matter what the original distribution is, if my sample size is large enough, the sampling distribution will actually end up looking normal. So you can see here, I start off with a uniform population distribution, an exponential population distribution, and a normal population distribution. If my sample size is 2, then my sampling distribution, indicated with the blue line here, starts to mimic the normal distribution. It starts leaning that direction, but it's not there yet. If my sample size is 5, it gets closer, but it's not there yet. The normal, if population is normal, it's already there, okay? You're already there right from the get-go. So if your population is normal, you're good right from the beginning. But if it's anything else, it starts, but it takes some time. If your sample size is 12, it's getting there, not quite there. By the time your sample size is 30, you're just about there. Okay? So if your sample size is large enough, then your sample starts to mimic a normal distribution. That is important. If your sample size is large enough, your sample starts to mimic a normal distribution. And with that, we can now state our central limit theorem. When taking a random sample of independent observations from a population that has a fixed mean and standard deviation, the distribution of sample means approaches the normal distribution as the sample size increases. Okay, let me say that one more time. When taking a random sample of independent observations from a population with a fixed mean and standard deviation, meaning When you're taking a sample from any population, regardless of the distribution, then the distribution of your sample mean approaches a normal distribution as your sample mean increases. There you go. That is your central limit theorem. Okay? I need you to remember the central limit theorem. Take it, study it, understand what it is. What you need to take from it is in the next few slides. First of all, these equations. I need you to take these equations from it. In the next video, we'll practice with these equations. I'll show you how they work, what we get from it. We'll cover that in the next video. But here are a couple of conditions that we need to take from the central limit theorem, okay? A sampling distribution of means will be normally distributed if, first condition for the central limit theorem, ready? Each sample is randomly selected. This is absolutely essential for the central limit theorem to be satisfied, okay? Each sample has to be randomly selected. This is needed for things to become normally distributed. Second, now go back and look at the wording of the central limit theorem and you'll see why this is needed. Second, the sample needs to be large enough. Large enough for the sample to become normally distributed. How is that worded? For the distribution of means to approach the normal distribution. Okay, so the sample needs to be large enough. In other words, your sample size needs to be at least 30. Okay, when we get into stuff starting next week, these two conditions, sample being randomly selected and sample being large enough, absolutely have to be met. Absolutely have to be met. Okay? There will be some cases where the sample being large enough, we can let that slide if the parent population is normal. Again, that happens if the population is normal, then smaller samples will be normally distributed right from the beginning with smaller samples, okay? So that will work. If those two are satisfied, then we can go through, then we can use these equations, and I'll show you those again in the next video. Now, everything I have shown you up to this point in all of these videos is if we are dealing with quantitative data. I have not even touched categorical data. I won't derive any of these equations for you. Just know that there are similar derivations for them as well. But let me just show you how, very briefly, what these would be. First of all, a sampling distribution of proportions will be normally distributed if each sample is random, same story, and a sample is large enough if n times p, this would be the number of successes, the number of successes, I'm sorry, I hit the button there, number of successes is at least 10, and n times 1 minus p, this would be the number of fails, is also at least 10. Okay, I'll review this again when we get to that point. Also, the average of your sample proportion of successes is going to equal the proportion of successes for your population, and the standard deviation of your sample proportions of successes is going to follow this equation. Again, we'll go over this equation more in lesson 19. You will see it more later. I just wanted you to be aware of these as well, so that when the time comes, they're not unfamiliar. All right, and that does it for this video. Next video, we're going to practice with these equations.